Let's look at example 17.1. 17.5, sorry. So we have a car that's 2 megagrams, or 2 times 10 to the third kilograms. Has a center of mass at G, right here. We want to find the acceleration if the rear driving wheels are always slipping, so this thing's spinning and it's causing a force right here at what we'll call B. And we will call this A. Alright, the front wheels are free to rotate, so we can ignore them. Neglect the mass of the wheels, we can ignore that. In real life, each of these wheels has its own moment of inertia, but we're not worried about that just yet. The coefficient of kinetic friction between the wheels and the road is given as 0.25. So find the acceleration at point G. This thing is getting pushed. It's going to have some acceleration going off and to the left. So let's do a free body diagram first. We have, just going to draw a box with some G right there. We have a normal force acting at A and a normal force acting at B. We also have mass times gravity acting at G. Okay, if I sum the forces in the x direction, what do I get? Give me mass times the acceleration of G in the x, and so call positive to the right, then that force right here, oh, we missed one. The force applied at the tire that is pushing this thing. Sorry, it's applied down here. Everything touching it, including gravity. Alright, so we have in the x direction, we have a 0.25 times the normal force at B, and then a 2,000 kilograms times the acceleration of G in the x direction. We can get one more equation if we do the summation of the forces in the y direction. It's going to give us mass times the acceleration of G in the y. It is not coming off the ground or accelerating in the y direction, so we can cross that out and say we have a normal force, and the weight. So normal force at A plus the normal force at B minus mass times gravity is equal to 0. Alright, equation 1, equation 2. We can get one more equation. It's not going to give us anything, but if we sum the moments, since it's not rotating, there is no alpha, I alpha ends up being equal to 0. So we can say that because we know it's not rotating. Therefore, let's sum up the moments. We get a normal force at A. That normal force at A with respect to G was acting at 1.25 meters away. The normal force at B, and I'm going to give that a minus sign because this would give us a negative rotation. B is going to be a positive sign because it would give us a positive rotation, and it's the normal force at B acting at 0.75 meters. Alright, now the one that is missed the most is the fact that this distance is 0.3 meters. So that's another negative force of friction at B times the 0.3 meters, and all that's equal to 0. We know what this is. That is equal to the frictional force. So we have mu times the normal force at B. We know the normal force at B from one of our three equations, and we're done. We can solve all three to get the acceleration at G to be in to the left 1.59 meters per second squared. Then if you wanted to, you could figure out what the normal forces are. Comes out to be 6.88 times 10 to the third newtons at A, pushing up, and the normal force at B ends up being 12.7 times 10 to the third newtons. Alright, so this was a case where there was no rotation. We are looking at sections 17.1 to 17.3 right now. 17.4 is where we're going to say that the summation of the moments is equal to I alpha, but in this case that was 0.